Today we will discuss carbohydrates. Carbohydrates may be defined as polyhydroxyaldehydes or ketones or substances or those substances which yield these compounds on hydrolysis. So we can say carbohydrates are polyhydroxyaldehydes or ketones or those substances which yield these compounds on hydrolysis. The empirical formula of carbohydrate is CH2ON, where is not less than 3, where N is not less than 3. Carbohydrates can be classified into 3: saccharides, oligosaccharides, and polysaccharides. So we'll discuss one by one. Monosaccharides are simple sugars which cannot be further hydrolyzed under mild conditions. Simplest sugars that are simplest monosaccharides are glyceraldehyde and dihydroxyacetone. So this is aldehyde and this is ketone. So the formula is of glyceraldehyde is this, and the formula of dihydroxyacetone is this. So this is an aldehyde because of this carboxylic group, and this is ketone because of this group, that is ketone group. Oligosaccharides contains monosaccharides, 2 to 6 monosaccharides it contains, and they are joined by glycosidic bonds. So if 2 monosaccharides are joined, it is called disaccharide. If there are 3 monosaccharides, it is called trisaccharides. So likewise 4 tetra, 5 penta and 6 hexasaccharides. In some books you will find 2 to 8 monosaccharides are joined, and that forms oligosaccharides. They are hydrolyzable polymers of monosaccharides. Polysaccharides are long chain polymer of monosaccharides that may be either linear or branched. So if a polysaccharide contains all the monosaccharides which are same, it is homopolysaccharide, and if it contains different more than one type of monosaccharide, it is called heteropolysaccharides. Homopolysaccharides, heteropolysaccharides. Monosaccharides and oligosaccharides are crystalline compounds soluble in water and sweet in taste, whereas polysaccharides are usually tasteless, insoluble, with high molecular weights. So carbohydrates exhibit optical activity when a carbon is attached with 4 different groups. When a carbon atom has attached with 4 different groups, it is called asymmetric carbon or chiral center. So when a carbohydrate contains one or more asymmetric carbon, it exhibits optical activity. So these chiral carbons, they cannot be superimposed upon one another. However, they exhibit mirror image of one. So if we see so these asymmetric carbon or chiral center, they give mirror image, and if we take this and superimpose upon this, it cannot be superimposed. However, it shows mirror image. So these mirror image isomers are called enantiomers. These both the compound having same empirical formula, same structure, however they differ in one carbon mirror image, and they have same boiling point, same melting point, and same solubility in various solvents. However, and same optical activity. However, they differ from one another in one activity, that is optical activity. One enantiomer of the two rotate the plane polarized light into clockwise direction and said to be dextrorotatory. And the other counterpart rotate the plane polarized in light in anti-clockwise or counterclockwise direction, and that is said to be levorotatory, and this is exhibited by small d and small l. Monosaccharides can be classified based on number of carbon atom and based on the carbonyl group it contains. So it can be classified as aldehyde or ketone. So when it contains and also on the basis of number of carbon atoms it contains. So as we know that as the empirical formula of carbohydrate CH2ON, N is not less than 3. So we'll start. So if it is aldehyde and it contains 3 carbon, it is triose, 4 carbon tetrose, 5 pentose, 6 carbon hexose, and 7 and so on, pseudoheptulose, pseudo. So we'll see first simplest aldehyde is glyceraldehyde. So if we see here asymmetric carbon, the second carbon is asymmetric as all the valency, all the groups attached to it are different. So it will show mirror image. Its mirror image is so when hydroxyl group of last but one carbon is on the right hand side, it is D-glyceraldehyde. And when hydroxyl group is on the left hand side of the last but one carbon, then it is L. This D and L has nothing to do with small d dextrorotatory and levorotatory. This refers to optical activity, and this refers to the hydroxyl group is on the right hand side and left hand side of last but one carbon. So Want half gave the formula 2 to the power n for number of isomers, where n is number of asymmetric carbon or chiral center, chiral carbon. So here it is one carbon which is chiral carbon, and this other two are not chiral centers. So here 2 to the power 1 is equal to 2. So this glyceraldehyde has two isomers, D glyceraldehyde and L glyceraldehyde. So we'll see further how they are. So we'll see how this 4 carbon, 5 carbon, that is from triose, tetrose, pentose and hexose. So we'll just copy it. So in 4 carbon, if we add 1 carbon here, just this hydroxyl group will be added on the right hand side of the left compound, and on the left hand side of the right. So this is glyceraldehyde, and This is 4 carbon tetrose. So here if we see, there are 2 asymmetric carbons, the second one and third one. So 2 to the power 2 is equal to 4. So this is D-erythrose and D-threose. So similarly, L-glyceraldehyde will have L-erythrose and L-threose. Now we'll see how this 5 carbon pentoses are. We'll just copy it as we have copied it above. We can write it like this also. D-erythrose can be written like this. This line shows the hydroxyl group is on the right hand side. So if we write like this, this is also a convenient way to write. So we'll copy in. And we'll add 1 carbon at second carbon. And what we did in previous case, hydroxyl group on the right hand side of the left and hydroxyl group on the left hand side on the right hand compound. So similarly, we'll do here also. So we have added hydroxyl group on the right hand side and here on the left hand side. Here on the right hand side of the left compound and right hand side on the left compound and left hand side on the right compound. So if we see here, number of asymmetric carbon or chiral center, they are 3. So it will have 8 isomers. So this is D-ribose, this is D-arabinose, D-xylose and D-lixose. So similarly, we'll copy it for hexose and we'll add hydroxyl group on the second group. Second carbon we'll add and we'll have hydroxyl group on the right hand side of the left compound and left hand side of the right compound. So I'll name all the compounds of the hexose. In case of hexose, number of asymmetric carbon will be 2 to the power 4, so it will have 16 isomers. So if we see in case of pentose, 4 compounds here and similarly 4 compound in the L series. So similarly, in case of hexose, 8 compounds in the D and 8 in the L form. So I will name them. You can write. So first compound is allose, D-allose, D-altrose, D-glucose, D-mannose, D-gulose, D-idose, D-galactose, and D-talose. Moreover, this linear form projection was given by Fischer, so it is known as Fischer projection. So with this, I thank you very much for patience listening.